we started this particular topic of fitting linear model using matrices. And of course, we're not able to finish that. And because of that, and because this particular area is very, very crucial when it comes to final, I'm actually going to use this material. I'm going to start with this material today. So let's get started. Before I start, I've already uploaded makeup for midterm 2 in case you are interested, and I extended the deadline to Sunday. The moment if you are not ready to start, don't start, because I actually programmed that for like 60 minutes. So additional 10 minutes, you know, to give room for time for uploading. You get what I mean? So you can start at any time, but if you are not ready to start, don't start. And of course, it's not compulsory, it's not compulsory. So it's for those who want to improve on their midterm 2 grade, or those who miss the exam in the first place. Okay, so I want to welcome you to today's topic. And I also want to tell you I've been sharing the link of my recording. I shared some minutes ago, so you can check. So fitting linear model using matrices. I remember I told you the whole thing is going to start with model specification. Okay, this is the model specification. I'm actually assuming we got 2 variables. So this is simple linear regression. Y is dependent variable that we also call response. And X is explanatory variable that we call predictor. And of course, E is the error, and beta naught and the beta 1 are the regression coefficients. Now, I show you how we can write that in matrix form. The specification right now is not in matrix form. If I actually want to write that in matrix form, okay, I'm actually going to write X beta, okay, plus the error. This is a matrix specification of linear regression model. The very first one is a scalar specification. And of course, I've shown you Y is n by 1, okay? And you can see a design matrix S. You see a design matrix of, the vector for the error, and of course for the parameters. And of course, I show you this equation the other time. This is what we call normal equations. And let me just tell you how we came about all of that. If I want to solve, if I want to figure out the least square, if I actually want to obtain the estimate of the parameter using least squared, of course, this is a formula, okay, that we're going to use. I'm going to show you how we derive that, okay? Now, in this formula now, okay, it means I need S transpose multiplied by S. And since I've already started with the specification matrix for each of the variable, or what I'm just going to do is take a look at this now. I'm going to start from that. The S transpose. If this guy is X, this is going to be the transpose of that. So multiply that guy by that guy is actually going to give me this guy. Okay. And when that give me that guy, what I'm going to do, I have my S transpose X. Okay. Now the next is to get the inverse for that. So the inverse is what I put here. Okay. Getting the inverse for that. Now the next thing is, what about S transpose Y? Okay. S transpose, this is S transpose. This is Y. Okay. Multiply that how? I'm actually going to get that. Of course, like 1, 1, 1, 1 multiplied by 1 multiplied by 1, 1, 1 multiplied by Y2, you're actually going to see that that would be summation Y. and x1 multiplied by y1, x2 multiplied by, that will be summation xi, yi. That's right, so you have. Then the way you get that, and you're just going to multiply, um, you know, this guy, okay, by this guy, which is what you're doing here. When you do that, you're actually going to have a B cap, okay? The B cap is going to be 2 by 1, going to have two values, one for beta naught, one for beta 1. Okay, so, and let me pay attention to this guy here, okay? The inverse of the S transpose S. If you take a look at the first one, this guy is actually C00, okay? This is C01, and that is also, this is going to be C10. C01 and C10, they're going to be equal. And this is C11. We just wanted to take note of all of that. Okay, now let us now talk about the sum of square error in a matrix form. Of course, we've discussed sum of square error. Oh, sorry, something is mixing here. Okay, if you take a look at this guy, that's a sum of square error, right? Okay, the sum of square of the distance between the response, the actual response, and the predicted response. Okay, that's sum of square error is in scalar. How am I going to write it in a matrix form? Okay, and I need you to pay attention to that. Okay, now, generally speaking, this is a matrix form representation of that guy. Okay, which means if I wanted to find the sum of square error, okay, at times I use for transpose. If I write this, okay, I can also do this. Okay, it's the same. You can use that as transpose or the other one, doesn't matter. Now, if I ask you to get the sum of square error, of course, that is y transpose times y. You already know y, okay? And you know this guy, S transpose multiplied by y. But this guy, beta transpose, don't forget the one you got the other time was going to be beta naught cap and beta 1 cap, right? The one you actually got through this. Give me 1 second. The one you got here. You see that? That guy is going to be 2 by 1. Going to give you the beta naught cap and the beta 1 cap, which means the moment that guy is wrong, your sum of square error will be wrong. Because in the sum of square error, you need a beta transpose. Okay, if I want to talk about the transpose of this guy, of course, it's going to be this. Okay, if this is a column, the transpose of a column is going to get you a row. Does that make sense? Okay, that is a sum of square error in matrix form. Now, if you take a look at this, if I now want to generalize, if you take a look at this guy, that's a multiple linear regression. We got so many variables. Okay, and I told you if I want to write this in matrix form, don't forget, in matrix form, it's going to be x beta, where each of that is a vector plus the error. That is in the matrix form. But let me tell you this. If you don't want to look at it from a matrix form, if you want to get your least squared, you got beta naught to beta p, right? Then it means you need to differentiate. This is going to become if this is the model, if this is the model in scalar form, this is going to be the sum of square error, right? In scalar form. And when you have sum of square error, if you want to estimate beta naught, beta 1 up to beta p, you should be ready to use it using the least squared. You should be ready to go there, differentiate with respect to beta naught set to 0, respect to beta 1 set to 0, until you get to beta p set to 0. Does that make sense? Which means you're going to generate a lot of equations. But you know what? If we use the idea of a matrix, it's going to save our time. Take a look at this. I want to generalize now. I want to write a multiple regression model in matrix form. I first start with Y, right? My design matrix S is going to change. Okay, I got X1 up to XP. Take a look at that. There, the numbers of independent variables is P. And if you look at the dimension of the matrix, it's going to be N by P plus 1. Why is it N by P plus 1? The N is the number of observations. P plus 1 is the numbers of parameters. Do you know that plus 1? That plus 1 is the intercept. You got to forget you're actually going to have X1 to XP, right? What about the intercept? Take a look at that. Okay, this is going to be the beta now, beta 1 to beta P. The matrix is going to save us a lot of time where we'll be able to get all the regression parameters in just one spot. Now, this is going to be the error. And of course, the matrix specification of modules of multiple linear regression model becomes that whether you're talking about simple linear, where two variables are involved, or you want to talk about multiple, where so many independent variables involved. The specification in matrix form remain the same, but specification in scalar form is not the same. For scalar form, it's just going to be y equal beta naught plus beta 1 s plus the error for one explanatory variable. And for so many explanatory variable, of course, the scalar specification is going to be this guy. Does that make sense? Okay, now the next thing I want to talk about is this. Like I said, the solution is this guy. If I want to estimate the parameters, whether it's a simple linear regression or for multiple linear regression, I'm going to use that. Okay, and we derive this from a normal equation, which I'm going to show you. But I first want to show you a practical example before I'm now going to go back, deriving this. Okay, so let me walk you through practical example now. Okay, let's assume that you're giving y to be this. Okay, how many observations do you have? 5, right? And you only have one explanatory variable, x1. X0 is a constant. Okay, so what you're saying there, you just only have one explanatory variable. Now, because you want to use this guy, okay, because you want to use that formula, okay, you need to first get the transpose of S, and after getting the transpose of S, you're going to multiply the transpose of X by X. When you multiply the transpose of X by S, that will give you this. And after that, you need the inverse. This is a 2 by 2 matrix. Of course, I'm going to allow you in exam to use a calculator. That's going to save time, right? So you can use calculator to get the inverse of 2 by 2, which is going to be this guy. After getting the inverse of that, which means I'm clear with this part. Then I need the S transpose Y, right? Okay, so this is my Y, and I can get the S transpose by transposing that. So multiply S transpose by Y, automatically, I'm actually going to get this. You can confirm all of this. The moment you get that, then you're actually going to use this guy here to multiply that guy. So you're going to use S prime S inverse to multiply S prime Y, which is what we're doing here. And automatically, that's going to give me the beta naught is going to be 1. The beta 1 is going to be 0.7. Do you remember the other time when we did not use matrix, we still get the same result for beta naught and the beta 1? Is there any question? So the beta naught cap is 1. the beta 1 cap is 0.7. Now, if I'm specifying the module, now this is going to be the module. So this is my estimated. When you are specifying the module, you got to put cap on Y. When you specify the module without putting a cap on Y, that is not correct. Because there's a difference between Y and Y cap. The model is to do a job of a prediction. Like that's why you're going to have a predicted Y. And that predicted Y, if you don't want to write predicted Y, you can actually write expected value of Y. Does that make sense? Because we believe expected value of Y is actually going to be equal to Y cap. Does that make sense? Is there any question moving forward? So far so good, right? Okay, now take a look at this. Oh, give me a second. Um, let's go to the next one now. Now, we actually want to consider another form of model. You remember the other time I walk you through different kinds of models. Okay, this is a polynomial regression. Particularly, this is a polynomial of degree 2. Do you know that linear regression is a polynomial of degree 1? And this is a polynomial of degree 2. When you take a look at this guy here, this guy is actually in addition to considering linear effects, this is also considering quadratic effects. Okay? And what measure the contribution of linear effect is beta 1. What measure the contribution of quadratic effect is beta 2. Do you know that we still have one predator? Except that we're looking at the linear effect of the predator and quadratic effect of the predator. Don't forget, x squared is based on x, right? Okay, now I need you to take a look at this example now. This is what you're given. They gave you y to be that, and they gave you this. Can you see that? Can you see your design matrix right now? X0, x, and x squared. You see that, right? Now, when you have all of that, you're still going to use, because this is linear model. Okay, I'm actually going to say, somebody may want to argue this with me, but this, how can I call polynomial equation linear? Oh, I'm actually calling this linear because I'm going to tell you right now, I'm calling this guy linear because it is linear in parameter. You can see beta 0, beta 1, beta 2. We did not square them. We did not put square root on them. We did not, that is linear specification of parameters. This is even though it is not linear in variable. Like look at x squared. That doesn't matter. That doesn't change the architecture to be non-linear. Okay, this can still be we can see estimate the parameters using linear framework. Okay, so if that happens, it means I can still use the same formula. Give me 1 second. I can still use this guy. Okay, now all what I just need to do, what is my S transpose, so like and so on like that, which I'm going to show you now. I'm going to get this guy. If you take a look at this guy, okay, this one is this guy here. That is the X, right? If I know the sign matrix X, the first one is a transpose of because I want to do S transpose X. When I multiply, like I said, I'm actually going to allow you to use calculator because this is going to take time if you want to do it manually. Even me, if I write the exam, it could take forever. So that's why I'm going to allow you to use calculator. So S prime S is going to be that. Go ahead. Yeah, can scientific calculator handle inverse of a matrix up to 3 by 3? Then if it is not, then I'm going to allow you to use, the graphing one then. Because I'm going to allow you to use a calculator that will allow you to be able to find inverse of 3 by 3. Does that make sense? Okay, now after that, the next thing that I'm actually going to do, okay, is to get the S prime Y. And after that, I find the inverse of that. Then in the end, then I actually use that. What am I telling the world right now? What am I telling the world right now? I'm trying to say my beta naught is the first one, my beta one is the second one, and my beta two is the third one. Let me tell you this. I'm actually going to do something now. Do you know that we're still working with this guy? Right here, we only consider linear effect, like we did not consider quadratic effect. Now, considering linear effect, without considering quadratic effect, we believe quadratic effects is not going to be significant. But here we now want to see if we consider quadratic effect, okay, what is going to happen? Now, when we consider quadratic effect, you're actually going to see initially the beta one is still it was 0.7. If I go back, yeah, let me see if it is the same question. Okay, now here, um, the intercept is 1. Initially, the beta 1 is 0.7. Now, when we incorporate quadratic effect, the intercept changes from 1 to 0.571. The slope still remains the same, and we now have a quadratic term. And of course, we're actually going to look at, further analysis we need to be carried out to be able to see whether the quadratic effect is significant. Okay, so we're still going to talk about all of that. Now, this is going to be the end of this material, and I'm going to show you another material. And after the material, then I'm going to come out with some derivations. What I'm only going to show you the derivation is how do we derive the formula we're using, that formula. How do we derive it? I'm going to show you. Okay. Now I'm going to stop my share now.